Welcome to the lecture series on CFD, Part 1. This is Lecture 8 on Advanced Finite-Volume Methods. In this lecture, higher-order approximations for finite-volume methods are described. First, Simpson rule for surface integrals in 2 and 3 dimensions are described, including the proof for fourth-order convergence. The next steps are higher-order interpolation methods, which are required to retain the fourth order of integral approximation when computing convection fluxes. Described are both standard and compact fourth order approximations based on polynomial fitting, including the Taylor series analysis to confirm the fourth order. Finally, standard and compact fourth order approximations of gradients at control volume faces are presented, which are needed to achieve fourth order approximations of diffusion fluxes. At the end, I'll also present numerical experiments by which the overall order of flux approximations and discretization errors for various combinations of approximations are analyzed. The integral over the closed control volume surface is equal to the sum of integrals over its faces. For the sake of simplicity, we consider an arbitrary function f and show how it can be numerically integrated over the face sk with order higher than second order of midpoint rule presented in the preceding lecture. In our transport equation, f stands for the flux vector component normal to cell face. In the convection term, f is the product of density, transported variable phi, and the normal velocity component. In the diffusion term, f stands for the product of the diffusion coefficient gamma and the gradient vector component normal to cell face, which is the derivative of phi with respect to n, the local coordinate directed normal to the cell face and pointing outward. Finite volume methods of higher order require for both convection and diffusion fluxes 2 levels of higher order approximation. Approximation of surface integral over the cell face with higher order quadrature formula, interpolation of the function phi to integration points in the cell face using higher order methods in the case of convection flux, or approximation of the derivative of phi in the direction normal to cell face at integration points using higher order methods in the case of diffusion flux. The second order midpoint rule approximation assumes a linear variation of function f over the face. For a higher order approximation, we have to assume a polynomial of a higher degree. Let us see what happens if we assume a quadratic variation of f along the east face in a two-dimensional case. To obtain the free coefficients, we need to fit the polynomial to function values at 3 points. The obvious choice is the face center E and the two corners SE and NE. Because all variables are computed and stored at cell centers, we need to use interpolation to obtain the function f at the free integration points in the cell face. We define a local Cartesian coordinate system at the cell face with its origin at face center E. The y-coordinates of the other two integration points are minus delta y half for SE and plus delta y half for NE. By fitting the parabola to function values at these three integration points, we obtain these three expressions. The first expression defines the coefficient A0, while the other two make a system of two equations with two unknowns, A1 and A2. By summing these two equations, we eliminate A1 and obtain an expression for F2, which is shown in the next slide. This is the resulting expression for A2. We don't need to determine A1 because it drops out when we integrate the parabolic function f along the face from SE to NE. Because the integral limits are of the same magnitude and opposite sign, terms with even powers of y cancel out when limits are applied, leaving in the end the following expression for the surface integral over face E. The mean value of the function on face E is now approximated as 1/6 of the sum of two corner values and 4 times the midpoint value. This is the well-known Simpson rule for numerical integration in one coordinate direction. Let us now find an expression for the leading term in the truncation error of Simpson rule to check its order of approximation. We consider again the east face of a control volume with a local Cartesian coordinate system set at the face center E. Now we write the Taylor series expansion along y coordinate for f centered around the location E. H contains all higher order terms. We apply the Taylor series expansion to the function values at NE and SE points, whose coordinates are delta y half and minus delta y half. When we add these two equations, we get rid of terms involving odd derivatives. From the resulting equation, we can extract an expression for the second derivative at phase center E, shown in the next slide. This is the resulting expression for the second derivative at phase center E, in which terms involving the sixth and higher even derivatives of f are omitted. Now we integrate the Taylor series expansion of f along the phase E, from SE to NE. The derivatives of f at phase center E can be considered as constants, so the integration is straightforward. When we apply integration limits, all terms involving even powers of I drop out, leading to the following expression. The first term on the right hand side is the midpoint rule approximation. We obtain a high order approximation by replacing the second derivative with the above expression. After some rearrangement, we obtain the following expression for the integral. The first term on the right hand side is the Simpson rule approximation, and the next term is the leading local truncation error term. All high order terms are contained in H. The local leading truncation error term is proportional to delta y to the power 5, but when we do grid refinement, we have a finite integration domain with n segments, and n doubles when the grid is halved. Because the error is incurred n times, and n equals s over delta y, the global error is proportional to delta y to the power 4. This means that the Simpson rule is a fourth order approximation. It is interesting that the assumption of a linear variation of the function f led to the second order midpoint rule, while the assumption of a quadratic variation leads to the fourth order Simpson rule, isn't it? The increasing complexity of the integral approximation from second to fourth order is not too large in 2 dimensions, but let us see what happens when we consider 3-dimensional grids. In the case of a 3-dimensional grid, surface integrals require integration in 2 coordinate directions. In 2 dimensions, we obtain a fourth order integral approximation by assuming a parabolic variation of integration function along the face. For faces of a 3-dimensional Cartesian grid, we can use biquadratic shape functions, for example this one, with 9 coefficients. When integrating over the face E of a Cartesian control volume, from minus delta y half to plus delta y half, and from minus delta z half to plus delta z half, many terms drop out, and we obtain the following expression for the integral. By fitting the above shape function to variable values at 9 integration points, the face center, center of each edge, and the 4 corners, we finally obtain the following approximation of the integral. This is the fourth order Simpson rule for integration in 2 variables. It requires function values at these 9 integration points. To retain the fourth order of the integral approximation, all these variable values have to be obtained from cell center values by at least fourth order interpolation. We see that in 3D cases, the complexity is substantially increased from midpoint rule to Simpson rule. This is especially true for non-Cartesian control volumes. While midpoint rule works for any shape, the above Simpson rule approximation works only for rectangular cell faces. It is even more complicated when we turn to volume integrals. In 2-dimensional problems, a fourth order volume integral approximation corresponds to the surface integral approximation in 3D case. Thus, the formula derived in the preceding slide can be used. Interpolation of at least fourth order is required to compute the variable values at face centers and cell corners to retain the fourth order of the volume integral approximation. For a 3-dimensional Cartesian control volume, the fourth order Simpson rule for volume integral approximation requires 27 integration points. Cell center, 6 face centers, 12 face edge centers, and 8 cell corners. Except for the cell center, all other variable values need to be obtained by interpolation. Deriving high-order approximations of volume integrals for non-Cartesian control volumes is therefore very complicated. Let us now see how high-order interpolation methods can be derived. In many codes, quadratic upwind approximation, also known as quick scheme, is available. Quadratic interpolation requires fitting two variable values at 3 points to determine the free coefficients, 2 upstream cell centers and 1 on the downstream side. This means that at every cell phase, one needs to check the flow direction to determine which cell is on the upstream and which on the downstream side. For the flow direction indicated by the blue arrow in this figure, cell centers P and W are on the upstream side and E is on the downstream side. This is the interpolation formula, valid for both uniform and non-uniform grids. D denotes the downstream cell center, U the first upstream cell center, and UU the second upstream cell center. The coefficients G1 and G2 are computed from cell center coordinates using these two expressions. On a uniform Cartesian grid, assuming U greater than 0, the coefficients are 6/8 for the first upstream node, 3/8 for the downstream node, and -1/8 for the second upstream node. Framed in red is the leading truncation error term. It is proportional to grid spacing cubed, so the interpolation is third order approximation. This was also verified in numerical experiments presented in slide 18 of lecture 7. However, as shown in slide 19 of lecture 7, if this approximation is used together with midpoint rule approximation of surface integral, the convection flux approximation will converge with second order, the order of the midpoint rule integral approximation. Another option is cubic interpolation, that is, fitting the variable phi to a cubic polynomial. The 4 coefficients of the polynomial can be obtained by fitting it to variable values at 4 cell centers, 2 on the upstream and 2 on the downstream side. On a uniform Cartesian grid, this approach leads to the following expression for variable value at the phase center E. The order of this approximation can be determined by a Taylor series expansion. We write the series in x direction centered around the phase E and apply it to variable values at 2 upstream, P and W, and 2 downstream cell centers, E and EE. Here are the expressions for phi E and phi P. The other two are in the next slide. Here are the Taylor series applied to cell centers at W and EE. Now we add the expressions for phi E and phi P from the previous slide and the above expression for phi W and phi EE to eliminate the odd derivatives. The following two equations contain only even derivatives of phi. We multiply the left expression by 9 as subtracted from the right expression to eliminate the second derivative. This leads to the following expression. The blue framed part is the approximation from cubic polynomial fit presented in the preceding slide, and the leading truncation error term is framed in red. It is proportional to grid spacing to the power 4, so it is a fourth order approximation. This approximation is often called fourth order central difference. There are more options when we assume a cubic variation of the variable in the vicinity of the phase E. Instead of fitting the polynomial to variable values at 2 upstream and 2 downstream cell centers, one can also use variable value and its first derivative at the 2 cell centers on either side of the phase to determine the coefficients of the polynomial. The following fourth order compact expression for phi E is obtained on a uniform Cartesian grid. This is analogous to the derivation of compact Padé schemes for finite difference approximations described in lecture 5. Interestingly, if we replace the first derivative in this formula with second order central difference approximations, we obtain the approximation from the previous slide, here expressed as the second order linear interpolation plus the correction that raises the order to fourth. The same approach can be used to fit a parabola to 2 values at cell centers on either side of the phase and to the first derivative at the upstream cell center. This is then a compact version of the quick scheme. To obtain fourth-order approximations of diffusion fluxes using Simpson rule integral approximation, we also need to approximate the gradient at the cell face with at least fourth order. This can be achieved by fitting a cubic polynomial to variable values at 4 cell centers. The following expression is obtained on a uniform Cartesian grid at the face E. This approximation is called fourth-order central difference. If we fit the polynomial to variable values and first derivatives at cell centers on either side of the face, the following compact fourth-order approximation is obtained. The first term on the right-hand side is the second-order central difference approximation. The remaining two terms, underlined in red, represent the correction which raises the order to fourth. The same formula was presented for finite difference methods in Lecture 5. Note that for the same grid spacing as in finite difference methods, the compact approximations from this and the previous slide are applied over half distance, which results in higher accuracy. Compact schemes require implementation via deferred correction. For efficiency reasons, all high-order schemes are implemented in this way to keep the computational molecule limited to nearest neighbor cells. Let us now perform some numerical experiments to test the order of various approximations. For some schemes, we have derived expressions for the leading truncation error term, but this is not so straightforward to do for the complete flux approximation because it involves both the approximate integration and interpolation of differentiation. Numerical experiments are equally simple for linear and nonlinear terms. We test the order of various approximations by computing approximations of surface integral over a given area using systematically refined grids and variable values at cell centers taken from an analytical function. Here, the following polynomial function is used. Discretization errors are determined by comparing approximations with the exact value of surface integral obtained by the analytical integration of the function. Interpolation and approximation of cell face gradient are included in integral approximations. The order of interpolations based on quadratic and cubic polynomial fit was proven in slide 18 of lecture 7. This figure shows the two-dimensional coarse grid and two levels of refinement. Integration area is the east face of one coarse grid cell, shown here by the thick red line. Each time the grid is refined, the number of faces over which the integration needs to be performed doubles. And all these integrals are summed up so that the integral over the same area on all grids can be compared. This slide on the left shows the variation of the computed convection flux through the total integration area with grid refinement, and on the right the error in the numerically computed integral. Simpson rule is used to approximate the integral, and 5 different ways of computing the variable value at the integration points, face center and face corners, are used. Exact value at integration points from the analytical function, labeled analytic, which gives the error of the integral approximation alone. Linear interpolation, labeled CD2, quadratic interpolation, labeled quick, cubic interpolation, labeled CD4, and compact fourth-order interpolation, labeled PADE4. We see that all approximations converge monotonically toward the exact value. Quick approximation underestimates and all other overestimate the exact value on coarser grids. As expected, the error reduces 2 orders of magnitude when grid spacing reduces 1 order of magnitude if the second-order linear interpolation CD2 is used to compute the variable values at integration points. The fourth-order approximation of integral, the Simpson rule, with 3 integration points loses its accuracy if variable values in integration points are not obtained with at least fourth-order interpolation. This is confirmed by using quadratic interpolation, quick, to compute the variable values at integration points. Now the error is reduced 3 orders of magnitude when the grid spacing is reduced 1 order of magnitude. We have here third-order convergence, the order of interpolation. Only when we use fourth-order interpolation by cubic polynomial, CD4 or the compact version, or when exact values from the analytical function are used at integration points, we obtain the fourth-order convergence of the convection flux term shown by the red, green, and golden lines. The errors are somewhat smaller when the exact values are used. The compact scheme is very close, but the slope is the same as in the case of CD4 scheme. At the finest resolution tested, the errors from CD4 are 3 orders of magnitude smaller than errors from CD2 and 2 orders of magnitude smaller than errors from QUIC. Thus, Simpson rule with cubic interpolation delivers by far the most accurate result. This slide shows on the left the variation of the computed diffusion flux through the total integration area with grid refinement, and on the right the error in the numerically computed integral. Simpson rule is used to approximate the integral, and 4 different ways of computing the gradient at the integration points, phase center, and the 2 corners are used. Exact value from the analytic function labeled analytic, second order central difference labeled CD2, fourth order central difference labeled CD4, and compact Padé approximation of fourth order labeled Padé4. We see that all approximations converge monotonically toward the exact value. All underestimate the exact value on coarser grids, except when exact analytical values are used at integration points. When the gradients at integration points are computed using second order central difference, CD2, the 2-level flux approximation also converges with second order, as the blue line shows. The error reduces 2 orders of magnitude when the grid spacing is reduced 1 order of magnitude. The lower order of gradient approximation overrides the high order of integral approximation. Approximation of the derivative at integration points with 4th order schemes, CD4 or Padé, leads to 4th order convergence of diffusion flux approximation, as the red and golden lines show. The compact scheme is more accurate, and the lowest errors are obtained when exact variable values at integration points are used. With the finest resolution used, the errors from 4th order approximations are approximately 4 orders of magnitude smaller than when gradients are approximated using second order central differences. Let me now briefly summarize this lecture. If it is expected that modeling errors are significant, then second order discretization is a good compromise between accuracy and complexity. Methods of higher order than second are desirable when very accurate solutions are required. Higher order methods require a sufficiently fine computational grid. When the grid is too coarse, they may produce larger errors than lower order methods. The problem with high order finite volume methods is that they have many integration points and that all approximations must be of the same high order. Approximations of surface and volume integrals, interpolation from cell center to integration points at CV faces, and approximation of gradients at all integration points. If for any of these approximations a method of lower order is used, the overall order reduces to the lowest order used in any of these 3 steps.